Welcome to chapter 13. We're now talking about light and reflection, and the first section is section 1 on the characteristics of light. So what we are going to do today is we're going to identify the components or parts of the electromagnetic spectrum. We're going to calculate the frequency or wavelength of electromagnetic radiation. We're going to recognize that light has a finite speed, and we'll describe how the brightness of a light source is affected by distance. So we've been talking about waves for the last couple chapters, and before we've only discussed mechanical waves, but now we're going to learn about electromagnetic waves. So remember, electromagnetic waves are a kind of wave that do not require a medium. So light can travel through a medium, okay? Or light or EM waves. It's easiest to think of light as an EM wave. But EM waves here, okay, they don't require a medium. Right? They don't have to, but they do go through them. So that makes sense, right? Because we can see the light travel through air, but it also travels through space. So it goes through both mediums and no medium. So what is an electromagnetic wave? Okay, well, an electromagnetic wave is a wave that radiates out from its source, right, where it started, at the speed of light, and we'll talk about that in a minute, and consists of oscillating, remember that word means to go back and forth, electric and magnetic fields. So this is like electric like electricity and magnetic like magnets. So it's kind of hard to imagine, but you can have magnetic fields without a magnet. And so the electricity, right, would go up and down this way. And then the magnetism goes up and down the opposite way, and they're 90 degrees to each other. So I don't know if you can see that in the picture, but the electro and magnetic waves are 90 degrees from each other. Okay, so you can kind of see it here if I drew. That would be our 90 degrees. Okay. So that is all that an EM wave is. It's just electricity and magnetism oscillating at 90 degrees from each other as it travels. And notice here, too, I want to point out that this is a kind of transverse wave. It doesn't have particles that travel up and down, but the electricity and magnetism travel up and down. So this direction is perpendicular to the direction the wave travels here. So that is why it is a transverse wave. So when we talk about electromagnetic waves, there's lots of kinds, and the most obvious one is light. But if we take white light and shine it through a prism, which a piece of glass, okay, that changes the direction of light is called a prism. Let me write this word for you here. Okay, if you do that, then you can actually see, and it breaks up the white light into all the different colors. Okay, so this is called the visible light because we can see it, it's visible. The visible light spectrum. But there's actually a whole bunch of electromagnetic waves outside of what we can see that have the same properties as light waves, in that they are electromagnetic. So here's just kind of a chart showing you all the different kinds of electromagnetic waves and their size. So see up here it goes by wavelength, okay, and frequency. You can kind of ignore these two in the middle. But wavelength and frequency are what you know. And some have wavelengths as big as a football field, and others are super, super small. And light here is kind of towards the small end, a little in between viruses and bacteria for how big the wavelength is, okay? And the frequency also varies greatly, okay? And you can kind of see all the different things we use it for, but I have a separate video for you to watch on the electromagnetic spectrum, so I'm not going to talk too much about it right now. So then as we talk about these EM waves, something important we need to talk about is the speed of light. And in the goals it said to recognize that the speed of light is finite, okay, as opposed to infinite, meaning it has a definite speed. Okay, whoops, it just ran out of room. Let's write that, definite. Okay, so it has a maximum value, okay? And this speed of light, we mathematically use the letter C for, okay? And, whoops, this didn't quite show. It should be 10 to the 8th up here, not 108. So 2.997 times 10 to the 8th meters per second. And sometimes we just abbreviate it as 3 times 10 to the 8th meters per second. So that's very, very fast. And what's really special about light is it turns out that this is the speed limit of the universe, meaning we know nothing that travels faster than the speed of light. Okay. So as we look at the speed of light, and I will fix this here too, we can actually use the same thing. C is a speed, right? So we often use V. And light also has wavelengths and frequencies. So we have our equation from before, where V equals F lambda. Okay. And now we can just replace V with C instead. So now we have C equals F lambda for light, or for EM waves. EM waves. Okay. But I do want to point out that this is the speed in a vacuum, or in space. It is the fastest light can go, but light can go slower. Okay, so that's important to know. Light can go slower. Sorry, I'm having trouble writing here today. Can go slower. Okay, but even if it goes slower, it goes like a very, very small fraction slower, like 2.89 times 10 to the 8th meters per second. Not a whole lot slower. And it mostly travels slower in matter. Okay, so in space it travels the fastest, though. So when we talk about light, we need to notice that it's brighter right next to light rather than farther away from it. So why is this? Well, this has to do with something called illumination, okay, or illuminance. So illumination and illuminance, they're kind of the same thing. And we say that the illuminance decreases as the square of the distance from the source. So if you take this source and you go out a distance of 1, right, it's going to decrease by 1. If you go out a distance of 2, the luminance is going to decrease by 1/4 because it's 1 over the square of the distance. So this has to do with the power that is put out by the light and the rate that it is emitted. Rate, remember, has to do with time. And the rate is called a luminous flux. Flux means something is flowing. Okay, so we would say that light flows, or as light is emitted. And it's measured in lumens. And we're not going to do a lot of calculations with this, but you should at least recognize these vocabulary words. So as we take a look at why this happens a little bit closer, just like with sound waves, we can talk about a wave front. Light has wave fronts too, where the wave front is just the crest of our transverse wave. And we can represent light also as having these rays. So here it has light rays. So we can represent it as just a line traveling out. Okay. So recognizing that then, if we take it and look at it this way, if you have some source of light, so S here stands for source, and you go out some distance, and here they're just using R for radius, or the distance, okay? And if you got one set of R, you might have like 9 points of light rays traveling through it, okay? So those same 9 light rays, as you can see, right, they're going out at angles from each other. So when you double that distance and you get out here now, right, here you had 9 in an area of 1 squared, right? Here now you've got 2 over R, and so we've got this area of 4. Okay, so now you have 9 rays in an area of 4. And you go out even further now to 3 times the distance. And now you've got 9 rays in 9 areas. Okay, so if you look at that, 4 is 2 squared, 9 is 3 squared. Okay, so it falls off as 1 over R squared, which is inversely proportional, right? But it's an inversely squared proportional. So remember that that is why. So here's another picture just to help you understand that a little bit more and to see it clearly. So when we're looking at this, what this is showing that as a circle gets bigger, every distance you go out, okay, the area squares. Okay, so sound actually followed the same pattern. Remember we had the equation for the intensity of sound? It fell off in the same way that light does because it's traveling outward in a circle from the source. Okay, and this picture here just shows graphically like how bright things get the closer you are to light. So this graph was drawn true to how much it is. So this would be considered darkness, right? And at a distance of 1, you've got that brightness. And then as you twice that distance here, so this is a distance of 2, it's 1/4. And so you can see they've changed the color. 1/9, 1/16, right? And this is a distance of 1, 2, 3, 4, 5, so on all the way to 10, right? So you can see how quickly light actually gets dark the further away from it you go. So that brings us now to the end of section 1. Let me know if you have any questions, and I will see you in class.